Hello. In the previous video about the interference of light, we had discussed that we have obtained this condition for superposition of two waves. Now, all of that you see on your screen right now, that is the conditions that we have obtained. That's a lot of things that we have discussed in that single page. Uh, in case you won't be able to get it, you'll have to go back to the previous video to obtain the condition. But what we have obtained from it is something like this, that the amplitude or the resulting amplitude of the superposing waves, that is given by a1 squared plus a2 squared plus 2a1 a2 cosine of phi, where phi, and that all of that under root, and phi here uh, is the phase difference between those two waves. Phase difference, as I said, that has been dealt with in waves, where one wave may be ahead or behind by a certain angle when you are measuring it in terms of angle. Well, we'll also be considering the case of path difference in this video. Now, from that, what we had also obtained is that the intensity. Now, the resultant intensity of the two superposing waves is given by the addition of the two intensities I1 plus I2 plus 2 times of root over of I1 root over of I2 cosine of phi, where intensity is obviously is proportional to the square of the amplitude, and so we have I1 and I2 as being proportional to the squares of A1 and A2, and also uh, we can bring in a constant over there, and we have this relation. This is a generalized relation of intensity, which we have obviously used over here. Now, with that, we have obtained the maximum amplitude in the case where the angle or the phase difference phi is going to be 0 degrees, and 0 degrees, or we can say phi is simply equal to 2n times of pi, where 2n is the integer which is varying from 0, 1, 2, and likewise, and pi is obviously 180 degrees. So this is 2n pi. This covers the 0 degrees as well. So let me just erase that. So that's the condition where we are getting the maximum amplitude, which is equal to the sum of the amplitudes directly, that is a1 plus a2, because cosine of phi has gone to 1, with phi taking up this value, the phase difference being equal to 2n times of, or the even multiple of pi, that is 180 degrees. And then again, you have the case of minimum amplitude, and the minimum amplitude in this case is going to be a1 squared plus a2 squared minus of 2a1 times of a2, and the minus sign comes in for the least value or the minimum value of cosine phi, which is equal to -1, when we have phi to be an odd multiple. Well, the odd can be taken as plus or minus. We are just considering the case of 2n plus 1 instead of 2n minus 1. We'll discuss about that negative sign later. So this is 2n plus 1 times of pi. That is going to be the value for n, again being equal to all of these values, that is 0, 1, 2, and likewise. Now, this will result in the value being equal to a1 minus a2, or a2 minus a1, doesn't really matter. Whichever is greater, you can just subtract the other one from that. And with the maximum and the minimum amplitudes available, you can obtain the maximum intensity, which is equal to the from this general relation that we have over here, that is k times of a squared. From that relation, we have k times of a squared. Instead of a, we can use a max over here, so a max squared. So this is equal to k times of a1 plus a2 squared, and then the minimum intensity is k times of a minimum squared, which is equal to k times of A1 minus A2 squared. Now, having obtained the condition for the maximum and the minimum intensity, consider the case where we have the amplitudes to be the same. Let us say we have A1 to be equal to A2, and let's say that is equal to A. And in that case, what we are going to get is that the I maximum is going to be equal to somewhat k times of 2a squared. Instead of a1 plus a2, they are going to add up as a plus a, which is resulting in 2a, and that will give me somewhat 4k times of a squared. We'll keep that value as of now. Then we have the minimum intensity, and that is going to be equal to k times of a minus of a, which is going to be 0. So we are going to get a completely zero intensity, which means a completely dark region, because we are talking about the intensity of light wave. So this is going to be the maximum intensity, which is going to be a bright spot wherever that occurs, and the brightest of them. And obviously the dark spot is due to the minimum intensity going to completely zero value. We'll come back to this case when we'll be discussing more about this. Now, having obtained these conditions so far, we wish to now bring the relation between the between the phase difference and the path difference. Now here we are considering, let me use another ink for that. Here let us suppose we are using two different waves, where the first wave supposedly has already started over here. It's continuing, and we have a second wave down below, and I'm not showing the interference as of now. We are just concerned about those waves individually, and the second wave is completely taken in phase. We have this kind of an arrangement, and the wavelength of each of those waves is the same. Now what happens over here is that if you observe the first wave, and this is the second one, the first wave has traveled an extra distance which is equal to the wavelength. And obviously the wavelength, in this case, you have the phase, this first half, the top half, the crest, that represents the phase angle of 180 degrees, and the bottom half also represents the phase angle of 180 degrees. So a complete phase angle of 2 pi, that is 360 degrees. So when you have a difference in path difference between the two waves to be equal to the wavelength, the corresponding phase difference, the phase difference goes to uh, 2 pi radian, as obviously in radians. And what else we have? If we have supposedly a path difference of 1, then we'll have a phase difference of 2 pi over lambda for any given wavelength. And in case we have a somewhat general value of path difference, let that be equal to x. In that case, we take the phase difference as 2 pi over lambda times of x, and that is taken as the phase difference that we have been using, phi. So here we are saying that phi is the general value of the phase difference when the path difference between the waves is simply equal to x. And you put any value for that x, and you will obtain the corresponding phase difference. For example, if we have x to be equal to let's say lambda over 2, that is half of the wavelength, then in that case what you would obtain is that the phase difference phi would be equal to 2 pi over lambda times of lambda over 2, and those lambdas are going to cancel out, the 2's are going to cancel out, so you have a phase difference of pi, which means pi phase difference, as we have seen already, is an odd multiple of pi when we consider this case that I have encircled right now. Phi will be equal to pi means n will be equal to 0. So 0 plus 1, 2, and in case of n over here, we put n is equal to 0, so we get simply pi. So phi is equal to pi, which means the phase difference is equal to pi. And what we are going to get? We are going to get a minimum intensity in that case. So these are the conditions that we are bringing forward. So now we can say that for a given path difference, now here there's a space available over here, I'm using it. So for a given path difference, let's say x, that being equal to well, that we know that for a given value of phi, well, let's start from the beginning. Phi is equal to 2n times of pi. Also, that is equal to 2 pi over lambda times of a certain phase difference, path difference, I beg your pardon. So in this case, what's the value of path difference? Now 2 pi is going to cancel out on either side. So you have the value of x for what kind of condition? That's for the maximum condition, the maximum amplitude as well as the maximum wave, maximum amplitude and the maximum intensity. So x is equal to, in this case, simply the lambda cross multiplies over there, and we have n times of lambda. To keep it to a value that we'll be requiring, we'll use an even multiple of lambda over 2. Even multiple of lambda over 2 is what we get for the path difference in case of maximum intensity. Now what about the minimum intensity? Well, minimum intensity, as you can see, we have the odd multiple term over here. Similarly, we can say that x, the path difference, having a value of an odd multiple of, again the odd is taken as 2n plus 1 instead of 2n plus or minus of 1. I'm just using the case of plus 1. I'll discuss that later why. So 2n plus 1 lambda over 2. So this is the condition for minimum intensity when the path difference is an odd multiple of the half of the wavelength, and when it is an even multiple of the half of the wavelength, we will get a maximum intensity over there. So all of this is what we determine in case of the conditions for the maximum and the minimum intensity. We'll be using these conditions in various aspects that we are going to discuss in further discussion of wave optics. But that's for the next video. Till then, thank you for watching.